So here is the summary of the given data. For the material X, we have initial cost at 15,000 ringgit. The maintenance cost is 9,000 ringgit per year, and the salvage value is 2,000 ringgit. For the material Y, we have initial cost at 35,000 ringgit. For the maintenance cost, 7,000 ringgit per year, and the salvage value is 20,000 ringgit. Both of this material have a 5 years lifetime and have 12% of interest rate. At the first glance, material Y looks attractive because the salvage value is very high, but we must evaluate using PW and AW analysis to make a fair economic comparison. So this is the calculation for the material X using present worth and annual worth calculation. For the present worth calculations, the formula given is the CO is initial cost, AM is for the annual maintenance, I is the interest rate, and the N is for the lifetime. As for the S is the salvage value. Then we have annual worth formula. So PW, present worth, I is the interest rate, N is the lifetime. After the calculations, we get present worth X is negative 46,308.13. For the annual worth for material X, we have negative 12,847.35. Next, we do analysis for present worth and annual worth for material Y. So after the calculation, the present worth for material Y is negative 48,884.90. As for the annual worth for material Y, it gets negative 13,561.66. Based on the analysis conducted, my final opinion is material X is the more suitable choice for spacecraft application. From the present worth analysis, material X has a present worth value of negative 46,308.40, which is higher or less negative than material Y's present worth. In economic decision, making the alternative with the higher present worth represents a lower total cost when all future expenses and salvage values are converted to present value. This result shows the material X requires less overall financial commitment compared to material Y. The annual worth analysis supports the same conclusion, which is material X has an annual worth of negative 12,847.35 per year, while material Y has a higher annual cost. This means that on a yearly basis, material X imposes a lower economic burden, making it more suitable for long-term spacecraft projects. If we choose the wrong material for spacecraft application, the consequences can be serious, especially in terms of cost and safety. First, from the cost perspective, selecting a more expensive material means we will spend more money than necessary. Aerospace projects already require a very high investment, and budgets are usually very limited and strictly controlled. If too much money is spent on one material, it can reduce the budget available for other important spacecraft systems such as propulsion, communication, or structural components. This can cause financial pressure on the project and may even lead to project delays or design compromises. Second, the wrong material choice can also affect safety indirectly. In spacecraft engineering, safety is highly dependent on proper testing. If more budget is used for material costs, less money may be available for critical safety-related activities such as preventive maintenance, system inspection, safety verification tests, and quality assurance processes. This situation can increase the risk of system failure, equipment malfunction, and or unexpected accident during the mission. Therefore, a poor economic decision can indirectly reduce safety margin and increase mission risk. From a sustainability perspective, selecting material X also supports efficient and responsible use of aerospace resources. In aerospace engineering, resources such as advanced material, fundings, and engineering manpower are very limited and extremely expensive. By choosing material X, which has lower present and annual cost, we can reduce long-term financial waste and use the available budget more efficiently. This means the saved budget can be allocated to other critical areas such as structural improvement, safety enhancement, and mission testing and system optimization.